What we're going to look at in this video. We're going to look at section 1.4 quadratic equations, and then we're also going to look at complex numbers. So we're going to start off with quadratic equations. And we're going to look at these four methods for solving quadratic equations. We're going to look at the quadratic formula. Actually, I'm not really going to look at that very much, but there's a formula, and remember you just plug in the numbers. But then we also have factoring, square roots, and completing the square. And I'm going to remind you what all of those mean. Quick little note about the quadratic formula is, remember, here's a quadratic equation in standard form. You have to put it in standard form. And the key is you have to make one side equal 0 before you find out what A, B, and C are. But once you know those, you just plug into the formula and solve. And so that's all I'm going to do with the quadratic formula. But let's take a look at factoring then. Let's remind ourselves about that. And because there is something, it's still pretty straightforward, but there is something that I do want to point out. Let's say that we had a problem like 4x squared. I don't remember actually what I gave you guys on your homework or the classwork on the first day of school. Well, let's say I gave you 4x squared plus 11x plus 6. And remember, the classwork that I gave you on the first day of school asked you to factor this. So let's factor this, because we're solving by factoring. Now, if you want to pause the video and try this on your own to see if you remember how to do it, go ahead. But I'll go ahead and do it right now and walk you through that Australian method that I showed you the first day. So, or I guess it was the second day that I showed you that. But remember, you set up your x. You put a times c at the top, which would be 4 times 6. You put b at the bottom, which is 11. And you want two numbers that multiply to the top and add up to the bottom. And those two numbers are going to be 3 and 8. They multiply to 24, they add up to 11. Divide by a, which is 4. And then simplify any of the fractions. 3/4 does not simplify, but 8 over 4 simplifies to 2 over 1, and then you have your answers. Read it from down under, bottom up. So the bottom goes with the x. 4x plus 3, there's one answer, or one factor. And 1x plus 2 is the other factor. So that's how you factor when a doesn't equal 1. That's a quick method. Now, what a lot of people did on the classwork is you made it equal 0, and then you set each factor equal to 0 and solved. And so we get 4x equals -3, or x is -3/4. And over on the other one, we know x is -2. So here's our final answer. However, what I've written now is wrong. And can you figure out what I have that is mathematically incorrect? And the thing is, I didn't have an equation to solve. There's no equal sign here. How can I solve for x when I don't even know what this thing is supposed to equal? It's just like saying this. It's just like saying, if I told you I had x plus 3, and you're like, oh yeah, when you got x plus 3, x equals 0. I mean, x equals -3. Well, you don't know that x is going to be -3 if all I told you was x plus 3, because again, I haven't told you what it equals. Does x plus 3 equal 0? Okay, then you're right. It would be -3. But what if x plus 3 equaled 10? Well, that's not going to be -3 now. Or what if x plus 3 equaled 100 or 1,000 or whatever? You have to know what the expression equals before you can solve for x. And it happens all the time. So don't feel badly if you're one of the people that did it. It happens every year. But just remember, until I actually tell you that this equals 0, you cannot solve this. There is no equation to solve. So make sure in your notes, if you're writing your own notes down, make sure that you put that equals 0 in the original problem. But once it equals 0, then you can do exactly what we did. Factor it, set each factor equal to 0, and solve. So there's factoring. Okay, now let's look at square roots. I mean, Why do we have that as its own thing? And really, there's just some problems that are easier to solve with square roots, but you can't, like, this is when you can isolate the x. If we go back up here real quick, I couldn't isolate the x until I got them down to just these linear equations. Then I could work on isolating the x. But I had to do something first. The idea with solving by square roots is that it's something you can already isolate the x in. So for instance, a really simple one, if you have 9x squared equals 36, now I can just do basic operations to start getting the x by itself. Divide both sides by 9, take the square root of both sides, I get the absolute value of x is 2, and x is plus or minus 2. So very easy to solve this way. I mean, I could have made the original problem equal 0 and either use the quadratic formula or factoring, but this is definitely the easiest method when you can isolate the x. If I have another problem, like quantity x plus 13 squared equals 25, I can still isolate the x here. I can take the square root of both sides. To get rid of that squared, I have the absolute value of x plus 13 equals 5. So x plus 13 is plus or minus 5. Subtract 13 from both sides. And now I actually have two equations to solve. Negative 13 plus 5 is negative 8. Negative 13 minus 5 is negative 18. Again, I could have gone to the original problem, FOILed out that x plus 13, subtracted the 25 to make it 0 in either factored or quadratic formula, but so much more simple to do this. So be on the lookout when you can just isolate the x. Let's do it. Here's a problem for you to try on your own if you want. It looks a little trickier, but you're going to find out that it's not. But think about how you would solve something like this. So I encourage you, pause the video, try this problem on your own, and we'll take a look at the solution together. Alright, so here's what you should have gotten on this one. I'll move it up, get that old one out of the way. So take the square root of both sides. You have the absolute value then on both sides. Now, when you have the absolute value on both sides, I mean, yeah, technically, I should have also had the plus or minus here on this side. So plus or minus x plus 5 equals plus or minus x plus 4. But when you look at all the combinations of pluses and minuses, you wind up with this. All you have to do is take one side and set it equal to plus or minus of the other. But that means we have two equations to solve. X plus 5 is the positive of x plus 4, or x plus 5 is the negative of x plus 4. And then this equation, the x's cancel out and 5 can't equal 4, so there's no solution for this one. But when you solve this one, you end up with negative 9/2. So we do have one solution here. Sometimes you get more, but in this case we only had one. So they're solving by square roots. So now let's look at the last method, completing the square. Alright, so completing the square can be really friendly on the right problems and then really ugly on the wrong problems. So like let's look at a really basic one. If I had x squared plus 6x minus 10 equals 0. First of all, with completing the square, if a doesn't equal 1, you have to factor out a. Whoa, I don't know what happened there. Come back. There we go. Oh, I have a stray mark there too. Okay. If a does not equal 1, factor out a first. And I'll show you what I mean by that. Okay, so, but in this case a does equal 1, so we're in business. So the next step then is to separate the variables and constants. Sorry about my cat here. So what I mean by that, the x is the squared term, squared variable, so we're going to complete the square on the x's. So anything without an x has to go to the other side. So we have x squared plus 6x that will leave, and we're going to move the 10 to the other side by adding 10 onto both sides. So now that we got that, now we're ready for the next step of completing the square. Now normally I would fill in that blank. Notice how I left a blank right here. Normally I would make use of that, but for purposes of the notes on this first problem, I'm going to just rewrite this line. So completing the square, remember you take half of b and square it. And so half of 6, b is 6, half of 6 is 3, and 3 squared is 9. So I'm going to fill in that gap with a plus 9. But whatever you do to one side, you have to do to the other. Now the reason why this works is because I've turned this thing into something that can be factored. And not only that, it can be factored into two identical factors. What adds up to 6 and multiplies to 9 is 3 and 3. So this is x plus 3, or x plus 3 squared. This is called a perfect square trinomial because you can always factor it into something squared. And the reason it's a perfect square trinomial is we followed this pattern. So it's kind of cool. And now, if you recognize it from the previous types of problems, now this is something that we can take the square root of both sides. So let me go ahead and write factor and simplify, which is exactly what I did. I factored to get the x plus 3 squared, simplified 10 plus 9. But now I'm just going to say square root and solve. So again, for purposes of the notes, I'm just going to rewrite this previous step and then show the square root on both sides. But we get the absolute value of x plus 3 equals root 19, which won't simplify, so x plus 3 is plus or minus root 19, and so x is negative 3 plus or minus root 19. And there's completing the square. So we're going to do a couple more of these. I'm going to give you one to try, and we'll take a look. So try this one. Try 5x squared minus 3 equals 20x, and see how you'll do there. If you can't, since a doesn't equal 1 on this one and you don't know exactly what I meant by that first step, I'll do that first step with you if you want, and then you can pause the video. Or you can just try it on your own right now. Pause the video. Okay, so what I'm actually going to do before I do that first step is, I can divide both. Well, I'll do that first step of getting rid of the a. I'm going to divide both sides by 5. So I'm going to have x squared minus 3/5 equals 4x. I've divided by a. Now go ahead and try completing the square on this one. Alright, so here it is worked out. I'll go through this real quick with you. So remember, we want to get the variables on one side and the constant on the other. And yeah, I got a fraction here, but it's not too bad. When I complete the square, half of b would be negative 2, but negative 2 squared is positive 4, so I added 4 on both sides. This factors into that. And then over here, combine your fractions. Think of 4 as 20 over 5, and 3/5 plus 20/5 is 23/5. Then we take the square root of this side, we get the absolute value. Oh no. I didn't take the square root of both sides. Silly me. Hang on. We're going to fix this problem together. I'm going to get rid of all this. See, we're all human. We all make mistakes. Haha. Alright, so we have, when I take the absolute value off, we're going to have plus or minus root 23 over root 5. I'm going to add 2 onto both sides, but I'm also going to, at the same time, rationalize the denominator here. So in a way, this is going to be easier, you'll find out. When I multiply 23 times 5, that is 115. Well, let me change back to pink. And then on the bottom we have a plain old 5. And we know that this square root will not simplify because it came from 23 times 5. That's the prime factorization. There's no two of a kind of factors. So we know that this guy won't simplify. It's nice to put this into a common fraction. So think of the 2 as 10 over 5. So we have 10 plus or minus the square root of 115 over 5. And in this case, we can't combine them anymore, so we're done. So there's completing the square in a nutshell. All right, and let's just kind of recap our methods. The quadratic formula, the benefit of that is it always works. It's not always the most efficient, but it always works. Any quadratic equation can be solved with the quadratic formula. So it can always be your fallback. But we know that factoring is really easy as long as the problem can be factored. So factoring, it's great when you can factor the problem. But if you can't factor it, you obviously can't use solving by factoring. Square roots. Square roots is also a super efficient method. But square roots is, you have to be able to isolate the x. So it's useful when you can isolate the x with square roots. And then there's completing the square. And by the way, completing the square, I'm always just going to abbreviate as CTS. So we can see on this last problem, it got a little more complicated than the example I gave you. Completing the square it always works. It's like the quadratic formula. Everything can always, and every quadratic equation can always be solved by completing the square. But when a doesn't equal 1, you got to factor it out, which could introduce fractions. And if b wasn't even, when you do that completing the square of taking half of b, then you can also run into issues with fractions. So completing the square always works, but it's best when a equals 1 and b is even. I'm going to do one more completing the square problem where a is 1 and b is even, and I want to show you how easy it is when both those conditions are met. In fact, I can fit it right here because this is all the space I'll need. So let's say we have x squared minus 10x plus 1 equals 0. So I can see a is 1, b is even. I'm going to separate my variables from my constants, so I'm going to move that 1 over to the other side. I complete the square by taking half of b and squaring it, so half of negative 10 is negative 5. Square it, we get 25. This factors into x minus 5 squared. This simplifies to 24. Take the square root of both sides. Square root of 24 is root 4 times root 6. So that's going to be 2 root 6, but it's plus or minus because I take the square root off. And so add 5 to both sides, and there's my answer. Very easy and straightforward when a is 1 and b is even. So there's section 1.4, quadratic equations in a nutshell. Remember we got 1.5 also. All right, so complex numbers. Let's first talk about what imaginary numbers are. So remember, imaginary numbers came from this whole dilemma of what the heck is the square root of negative 1? We don't know what it is. And we tried to figure it out, and it can't be a positive number because a positive times a positive won't give you a negative 1. Can't be a negative number because a negative times a negative is still not a negative. Can't be a 0 because 0 times 0 can't give you a negative. So, excuse me, what is the answer? And no real number works, so we have imaginary numbers. And it comes from this right here, that the square root of -1 is I. And it's a kind of a bad name, imaginary numbers, because imaginary numbers makes it sound like they don't exist in real life, but they do. There's actually a lot of engineering problems in electromagnetism, I believe it is, if I remember right, that imaginary numbers show up all the time. And so they're very useful, actually, in the real world, even though we call them imaginary numbers. Because a lot of students are like, if it's imaginary numbers, why do we even learn them? Because they have use. So that's why we do it. All right, so, and then we know we can go ahead and do something like the square root of -25 by breaking it up into root 25, root -1. Square root of 25 is 5, square root of -1 is I, so square root of -25 is I. So it turns out anytime you have a square root with a negative, you just tack an I on your answer. The square root of -49 is 7I. The square root of -100 is 10I. The square root of -27 is 3 root 3I. Now be careful about this one. This has to do with like handwriting again. When it's typed, this is the order you typically see it in. We put the I at the end. When you handwrite it, though, it's fairly common to see this 3I root 3. And either way is going to be okay when you're handwriting. The reason why, can you think about why we might do this when we handwrite? And the reason is this. If you're going to put the I at the end, be careful how you write it. Let me see if I can do this right. So let's say I have this. I don't know where the I is. Is the I in the radical or not in the radical? The way I just wrote it, it is not clear where the I is supposed to be. Inside or outside? It's supposed to be outside, but this doesn't look clear. And if you write something like this on a test, I will take off because it's not clear. Now, if you want to make it clear, you can do 3 root 3. Some people put a little hook. Or you can do what is done right here. Make sure that put the I in front. Or just make sure there's a good gap. But don't make it too big. If you make it too big, then it just, are you giving me two different answers? Are you saying root 3, or 3 root 3, and I as two separate answers? Or are they like this? That wouldn't be good either. So be careful here. Don't make it vague. And be careful here. Don't put it too far away. I know it's nitpicky, but it needs to be clear. It needs to be obvious what you meant. All right. So if we put, these are all imaginary numbers then. So we have real numbers, and then we have imaginary numbers. Oops. Can't spell imaginary. So real numbers don't have an I. Imaginary numbers do have an I. When we combine them together, we get what's called complex numbers. A plus BI. So there is a real part and an imaginary part to complex numbers. Now, all real numbers you can think of as complex numbers, believe it or not, because I can just put a 0I right there, and now I've made it look like a complex number. And the imaginary numbers, I could say 0 plus BI and say that's a complex number. So all real numbers are complex numbers. All imaginary numbers are complex numbers. But not all complex numbers are real, and not all complex numbers are imaginary. Real numbers don't have an I. Imaginary numbers, single term with an I. Complex numbers have both parts. Alright, so now we're just going to look at basic operations with complex numbers. Adding, subtracting, multiplying, and dividing. The good news is, oh, and powers. Let's look at the powers first. Powers of I. So starting with I to the 0, I to the first power, I squared, I cubed, I to the 4th, I to the 5th, I to the 6th, I to the 7th, I to the 8th. Let's see what happens here. So we know anything to the power of 0 is 1, and anything to the first power is itself. Now if I is the square root of -1, then I squared is the square root of -1 squared, which means it's just -1. I squared is -1. I cubed can be thought of as I squared times I. I squared we just said was -1, and so it's -I. I to the 4th we can think of as I squared times I squared, but we know I squared is -1, and -1 times -1 is 1. And look what happens. We're repeating the pattern again. I'm back up at 1. I to the 5th is just going to multiply by another I, so I'm just going to have this. So now I start to repeat myself. I to the 5th is the same thing as I to the first power, which is I. I to the 6th is the same thing as I squared, which is -1, and then we have -I, and then we have 1, and so on and so on. So then we can do any power of I. Like if I wanted to do I to the power of 51. Now you could follow this pattern until you get to 51, but it's going to take a while. But what you can also do is think of 51 divided by 4, which is going to be 12, with a remainder of 3. Because every fourth power is 1, and when you multiply by 1 it doesn't matter. Just look at the remainder. I to the power of 51 is the same thing as I to the third power, and we know, looking at this table, that I to the third power is -1. Think about this one. What about I to the 102nd power? I'll pause a little bit and let you think about that one. Okay, so think about dividing by 4. 4 would go into that 25 times with a remainder of 2, and I squared is -1. So that's how you do there. Nice. Yeah. Okay, so that's powers. Let's go ahead and look at adding and subtracting. Adding and subtracting is super easy. If you had, I'm just going to do this problem right here. Let's say 4i minus, we'll subtract this complex number, 5 minus 7i, and let's add this real number. And the beauty is, when you're adding and subtracting, it works just like variables. You don't even have to know anything about I. This could have been given in Algebra 1, or pre-algebra probably, when you were learning about combining like terms. Distribute that negative, combine like terms. Hopefully I don't make any arithmetic mistakes. And we get this. The only thing is, standard form for a complex number is a plus bi. And your answers should always be written in standard form, which means the real part first. 7 plus 11i. But otherwise it's just like variables. Doesn't matter. So that's adding and subtracting. Let's remind ourselves how multiplying works. Let's say I want to take a 3 plus I and multiply that by 4 minus 5i. Well, again, it works just like variables. There's one little tiny thing that will let you simplify a little more than if it was just an x. So we're still going to distribute. You can use the boxes or FOIL, like whatever method it was that you learned. I like to think of it as distribution. Excuse me. So the 3 is going to multiply by both of those. So 3 times 4 is 12, and 3 times negative 5i is negative 15i. And then I multiply the I times both parts. 4 times I is 4i, and negative 5i times I is negative 5i squared. And then we combine like terms. So the negative 15 plus 4i is negative 11i. So it hasn't been any different than if this was just variables, regular variables. The only difference is, remember from that table above, we said what I squared equals. I squared is negative 1, and negative 5 times negative 1 is plus 5, so we wind up with 17 minus 11i. We wind up with a complex number again. And you should always get complex numbers. Any operation with complex numbers should give you a final answer as a complex number. So here's one to try on your own. Let's do 2 minus 3i times 1 plus 4i. So give that a go, and we'll take a look at the answer together. Alright, so this is what you should have gotten. Let's take a look. Distribute the 2 across both of these, and you get 2 plus 8i. Distribute the negative 3i times both of these terms, and you get that. I combine the 8i and negative 3i, and I also did I squared is negative 1, negative 12 times negative 1 is positive 12, and then combined my like terms, and that's my final answer. So multiplying isn't so bad either. Just remember that I squared is negative 1. Alright, let's look at dividing. Now this one's a little different. So what if I had something, we'll do something simple at first. 2 divided by 3 minus I. And it's a fraction, but it's also division. So this is where we're going to do a little trick. It's a similar idea to rationalize in the denominator. We basically want to find a way to get the I out of the denominator, because if we can do that, we'll be able to write this as a complex number in standard form. So how can we get rid of that I? We can multiply by the complex conjugate. So, excuse me, complex conjugates, it's just like the radical conjugates we were doing before. If you have A plus bi, a minus bi is its conjugate. You just change the operation in the middle. So in this case, the conjugate of 3 minus I is 3 plus I. But I'm going to multiply top and bottom by that. So when I distribute in the top, I'm going to get 6 plus 2i. And in the bottom, remember when you multiply conjugates together, it's just like difference of squares backwards. A squared minus b squared is a plus b, a minus b. You're multiplying conjugates together. You can just do first times first and last times last to get that. A times a is a squared, b times negative b is negative b squared. So that's what I'm going to do here. 3 times 3 is 9. Negative I times positive I is negative I squared. But we know that I squared is negative 1, so that winds up being 9 plus 1, which is 10. And now I can write it in standard form by separating out my fractions, and then I should simplify. Whoop. And I wind up with that as my answer. So the key was multiplying top and bottom by the conjugate. You want to multiply by whatever it's going to take to get rid of the I in the bottom. And the conjugate can always work. And then you just work it out. So let me give you one to try on your own. And we'll do it together afterwards. Well, let me go to a new page here. So try dividing 4 plus I by 7 plus 2I. So pause the video, try that, and then we'll see what we'll come back together. All right, so let's try this one. Multiply by the conjugate, 7 minus 2I on the top and the bottom. So I'm going to be foiling that out, but on the bottom, first times first is 49. Last times last would be negative 4I squared, but again the I squared is going to change the sign and make it positive 4. So then I got 53 on the bottom. So now let's work on the top. So distribute the 4, distribute the I, and again I times negative 2I would be negative 2I squared, but the I squared makes it positive 2. Combine like terms in the top, and then write it in standard form. And there's dividing. Alright, let's just do one more problem and we'll be done with our notes. Woo, you guys are troopers. Let's just do a good old-fashioned solve. X squared plus 8x plus 40 equals 0. Use any method you want and solve it, and we'll come back and do it together. So you guys, pause the video, try it on your own, and we'll look at it together. Alright, here we go. So I chose completing the square because A was 1 and B was even, and I knew that would be nice and straightforward. So separate your variables from your constant, complete the square. Half of B is 4, 4 squared is 16, add that onto both sides. Factor and simplify. Now we got to get rid of the squared by square rooting both sides. Get the absolute value here. Here I'm starting to simplify, looking for that perfect square, and I also took out the negative 1. So when I take off the absolute value I get plus or minus, but now I have 2I root 6. Subtract 4 from both sides, I get my final answer. And you're going to get the same exact thing if you do the quadratic formula on this. This is just a lot faster, I personally think. Alright, there you go, that's it. I'll see you in class. Bye.